Now previously we have studied the ratio estimator using a single auxiliary variable x, and we have suggested different or discussed different almost unbiased ratio estimators. Unbiased in the sense they are unbiased up to first order of approximation only. So now we shall extend this to a multivariate ratio estimator case, that is when we have more than one auxiliary variable. So that means when we have adequate supplementary information or the auxiliary information, it is possible to improve on the ratio estimators. Now, three questions arise: whether the data on all the p greater than 1, auxiliary characters can be used to provide an efficient estimator of y bar. Now the second question, whether a ratio type estimator of y bar using p auxiliary characteristics is more precise than using q auxiliary characteristic, where q less than p. The third question, that means is it possible to estimate y bar more precisely using less number of auxiliary variables than p. Now the third question, whether a ratio type estimator of y bar using p auxiliary variables is more precise than the simple mean estimator y bar of y bar. So that means we have to compare this with the simple mean estimator, where we do not use any of the auxiliary information. We now use the multivariate ratio estimator suggested by Olkin and consider the above three questions first for the bivariate case, and then we shall examine it for the multivariate case. Now first let us consider the bivariate ratio estimator. In this type of ratio estimator, two auxiliary variables are used. Let y denote the variable under study and x1, x2 be the two auxiliary variables. A simple random sample of size n is selected from the population of n units, and we denote yi, x1i and x2i equal to 1 to n. This is the value of the study variable and two auxiliary variables for ith unit in the sample, and this is observed. Now the Olkin proposed the estimate y br bar, that is equal to w1 yr1 bar plus w2 yr2 bar, such that w1 plus w2 equal to 1 and yi bar equal to y bar by xi bar into xi bar I equal to 1 to 2. That means this estimator is based upon the first auxiliary variable, this estimator is based upon the second auxiliary variable. So here we assume that the population mean of both the auxiliary variables are known. x1 bar and x2 bar are known to us. So now, since w1 plus w2 equal to 1, we can write y BR bar, that is equal to W Y R1 bar plus 1 minus W Y R2 bar. So now we consider YPR bar minus Y bar equal to W YR1 bar minus Y bar plus 1 minus W Y R2 bar minus Y bar. So now Y R1 bar minus Y bar, that is equal to Y bar by X1 bar into X1 bar minus Y bar, that is equal to X1 bar by X1 bar into Y bar minus Y bar by X1 bar into X1 bar. So that is equal to X1 bar by X1 bar, this will be Y bar minus R1 X1 bar, where R1 equal to Y bar by X1 bar. Now setting X1 bar equal to X1 bar plus epsilon 1, we have X1 bar by X1 bar equal to, this is X1 bar divided by X1 bar plus epsilon 1. This is equal to X1 bar divided by X1 bar taking common, this is 1 plus epsilon 1 by X1 bar. So this is equal to X1 bar cancels out. So only we have 1 plus epsilon 1 by X1 bar inverse. So X1 bar by X1 bar equal to 1 plus epsilon 1 by X1 bar inverse. So that is equal to 1 minus epsilon 1 by X1 bar plus epsilon 1 square by X1 bar square plus up to so on. So that is 1 plus epsilon 1 by X1 bar plus order of epsilon 1 square. So we consider up to first order approximation only. So this is now, if n is very large, so we can have X1 bar by X1 bar, this is approximately equal to 1. So YR1 bar minus Y bar, that is equal to Y bar minus R1 X1 bar, and expectation of YR1 bar minus Y bar, that is equal to expectation of Y bar minus R1 X1 bar, that is equal to Y bar minus R1 X1 bar, that is equal to 0. Similarly, expectation of YR2 bar minus Y bar, this is also equal to 0. So we conclude that Y bar Ri, I equal to 1 to 2, these are approximately unbiased estimator of Y bar. Then Y BR bar is also approximately unbiased estimator of Y bar. So irrespective of the weights W. Now we choose the weights W1 and W2, that is W, so that the variance of YBR bar will be minimized. So that means we have suppose W1 equal to W, W2 equal to 1 minus W, so that W1 plus W2 equal to 1. So we have to minimize variance of Y bivariate ratio estimator YBR bar subject to W1 plus W2 equal to 1. So now variance of YBR bar, that is equal to expectation of YBR bar minus Y bar whole square for large n. This is equal to expectation of W1 R1 Y R1 bar minus Y bar plus W2 Y R2 bar minus Y bar. This is whole square. Now this is equal to expectation of W1 square into Y R1 bar minus Y bar whole square plus W2 square Y R2 bar minus Y bar whole square plus 2 W1 W2 Y R1 bar minus Y bar into Y R2 bar minus Y bar. So this will be equal to W1 square expectation of Y R1 bar minus Y bar whole square plus W2 square expectation of Y R2 bar minus Y bar whole square plus 2 W1 W2 expectation of Y R1 bar minus Y bar into Y R2 bar minus Y bar. Now this is equal to W1 square variance of Y R1 bar plus W2 square variance of Y R2 bar plus 2 W1 W2 covariance of Y R1 bar Y R2 bar. Let V11 equal to variance of Y R1 bar, that is equal to expectation of Y R1 bar minus Y bar whole square, that is equal to expectation of Y bar minus Y bar minus Y bar minus Y bar R1 whole square. So that is equal to expectation of Y bar minus Y bar minus Y bar by x1 bar into x1 bar minus y bar by x1 bar into x1 bar whole square, that is equal to expectation of y bar minus y bar minus r1 into x1 bar minus x1 bar whole square. So this is equal to expectation of y bar minus y bar whole square plus r1 square, expectation of x1 bar minus x1 bar whole square minus 2 r1 expectation of y bar minus y bar into x1 bar minus x1 bar. This is equal to variance of y bar plus r1 square variance of x1 bar minus 2 r1 covariance of y bar x1 bar. Now this is equal to one by n minus 1 by capital N sy square plus r1 square sx1 square minus 2 r1 syx1, that is equal to 1 by n minus 1 by n y bar square into sy square by y bar square plus xx1 square by x1 square minus 2 syx1 by y bar x1 bar, that is equal to 1 by n minus 1 by n y bar square, this will be cy square plus cx1 square minus 2 cyx1. So this is equal to 1 minus f by n y bar square cy square plus cx1 square minus 2 rho yx1 cy cx1. Now taking c0 square equal to c. Now let us replace 0, 1, 2 for y, x1 and x2. So variance of y11 will be equal to 1 minus f by n y bar square, this will be c00 plus c 11 minus 2 c01. So here c0 square equal to c00, c1 square equal to c11 and rho 01 c0 c1 equal to c01. This is also equal to c10. So now this is the value of V11. Similarly, the variance of Y R2 bar, that is equal to V22, that will be equal to 1 minus F by N Y bar square C00 plus C22 minus 2 C02. Now V12 equal to covariance of YR1 bar YR2. Now this is equal to expectation of YR1 bar minus Y bar into YR2 bar minus Y bar. That implies V12 equal to expectation of Y bar by X1 bar into X1 bar minus Y bar into Y bar by X2 bar into capital X2 bar minus Y bar. Now this is equal to expectation of Y bar minus Y bar minus R1 X1 bar minus X1 bar, just like previous, into Y bar minus Y bar minus R2 X2 bar minus X2 bar. Now after simplification we can get this is variance of Y bar minus R1 covariance of Y bar X1 bar minus R2 covariance of Y bar X2 bar plus R1 R2 covariance of X1 bar X2 bar. So this will be equal to 1 minus F by N into Y bar square C00 minus C01 minus C02 plus C12, just like proceeding as before. We can get, now we have obtained the value of V11, V22 and V12. Now we can use a function, because we have to minimize the variance of the bivariate ratio estimator. So we use a function phi that is equal to variance of Y BR bar plus this mu whole into summation I equal to 1 to 2 Wi minus 1. Mu is the Lagrange's multiplier, because we have to minimize this subject to the condition summation I equal to 1 to 2 Wi equal to 1, that is W1 plus W2 equal to 1. So this will be equal to W1 square V11 plus W2 square V22 plus 2 W1 W2 V12 plus mu W1 plus W2 minus 1. Now differentiating partially with respect to W1 and W2, this So del phi by del W1, that is equal to 0, and del phi del W2 equal to 0. This implies 2W1 V11 plus 2W2 V12 plus mu equal to 0, and this equation yields 2W2 V22 plus 2W1 V12 plus mu. This is equal to 0. Now this is equation 1, this is equation 2. Now from equation 1 we have 2W1 V11 plus 2W2 V12 equal to minus mu. That implies W1 V11 plus W2 V12 equal to minus mu by 2 equal to V, suppose. Similarly, from equation 2 we get W2 V22 plus W1 V12 equal to minus mu 2 by 2, that is equal to V. So solving these two equations, we get W1 equal to V12 by V22 divided by determinant of V11, V12, V21, V22. This is by determinant rule, and W2 equal to, this is V11, V12, this will be VV divided by V11, V12, V21, V2. So this W1 equal to V whole into V22 minus V12 divided by V11, V22 minus V12 square, and W2 equal to V whole into V11 minus V12 divided by V11 V22 minus V12 square. Since W1 plus W2 equal to 1, we have V divided by V11 V22 minus V12 square equal into V22 minus V12 plus V11 minus V12. This is equal to 1 using the value of W1 and W2. So that implies V equal to V11 V22 minus V12 square divided by V22 V11 plus V22 minus 2V12. So now using this value of V, we can again get W1 is equal to V11 V22 minus V12 square divided by V11 plus V22 minus 2V12 into V22 minus V12 divided by V11 plus V22 minus 2V12. So that is equal to V22 minus V12 by V11 plus V22 minus 2V12. Similarly, W2 is equal to V11 minus V12 divided by V11 plus V22 minus 2V12. So by putting these values of W1 and W2, we can get the minimum variance of bivariate ratio estimator. So the minimum variance of the bivariate ratio estimator is given by W1 square V11 plus W2 square V22 plus 2 W1 W2 V12. We put the value of W1 W2 here. So this will be V22 minus V12 whole square divided by V11 plus V22 minus 2 V12 square into V11 plus V11 minus V12 square by V11 plus V22 minus 2V12 square into V22 plus 2 into V22 minus V12 divided by V11 plus V22 minus 2V12 into V11 minus V12 divided by V11 plus V22 minus 2V12 into V12. Now we can simplify this, and simplifying we can get this minimum variance is equal to minimum variance will be equal to V11 into V22 minus V12 square divided by V11 plus V22 minus 2V12. This is the minimum variance of the bivariate ratio estimator. Now we shall compare comparison between the bivariate ratio estimator, the usual ratio estimator using a single auxiliary variable, and the simple mean estimator with no auxiliary variables. Now we shall compare between the following three types of estimators. Now a ratio estimator using two auxiliary variables, comparison between bivariate ratio estimator versus YR1 bar. Second, YR1 bar versus Y bar. Third, YBR bar versus Y bar. Now in these three cases we shall consider. Now in the first case, YBR bar versus yr1 bar means the bivariate case with univariate case. Ratio estimator using two auxiliary variables, ratio estimator using one auxiliary variable. So now here we assume that our study variable y is equally correlated with both the auxiliary variables x1 and x2, and the coefficient of variation of both the auxiliary variables is the same. So we have the assumption rho 01 equal to rho 02, that is equal to rho 0, and C11 equal to C22 equal to C square, that is C1 equal to C2 equal to C, and let rho 1 2 equal to rho. Correlation between the two auxiliary variables is rho. So under these assumptions we have V11, that is equal to 1 minus f by n y bar square, and this will be C0 square plus C1 square minus 2 rho 01 C0 C1. So that is equal to 1 minus f by n y bar square, this will be C0 square plus C1 square minus 2 rho 0 into C square, C0 C. Similarly V22 also equal to V11, that is equal to VC. Now V12, that is equal to 1 minus f by n y bar square into C0 square minus rho 0 C0 C minus rho 0 C0 C plus rho C square, that is equal to 1 minus f by n y bar square y bar square into C0 square minus 2 rho 0 C0 C plus rho C square, and here W1 equal to V22 minus V12 by V11 plus V22 minus 2 V12, this is equal to V minus V12 divided by 2V minus 2V12, that is equal to 1 by 2, that is equal to W2. So now variance of the bivariate ratio estimator BR bar, that is equal to V11 minus V22 minus V12, V11 into V22 minus V12 square divided by V11 plus V22 minus 2V12. So this will be equal to V square minus V12 square divided by 2V minus 2V12. So this will be equal to V plus V12 divided by 2. Now the variance of the bivariate ratio estimator is given by 1 by 2 V plus V12. this is equal to 1 by 2 V, the value of V already we have, that is B equal to V11 and also V12. The value of V is 1 minus F by N y bar square into C0 square plus C square minus 2 rho 0 C0 C plus V12. This is also 1 minus F by N y bar square. This is C0 square minus 2 rho 0 C0 C plus rho C square. Now this implies variance of bivariate ratio estimator YBR per equal to 1 by 2 1 minus F by N y bar square. This will be 2 C0 square minus 4 rho 0 C0 C plus 1 plus rho C square. This is equal to 1 minus F by N y bar square. This will be C0 square minus 2 rho 0 C0 C plus C square by 2 1 plus rho. Now variance of YR1 bar, that is also equal to variance of now for comparison we consider variance of R1 bar minus variance of Y BR bar, that is equal to variance of YR1 bar. This is 1 minus F by N y bar square. This will be minus C square by 2 1 plus rho plus C square. So that is equal to 1 minus F by N y bar square C square 1 minus rho by 2. So this is always greater than 0 because rho is less than 1 minus F by N, this is greater than 0. And this becomes equal to 0 when rho equal to 1. So therefore variance of R1 variance of YR1 bar is always greater than equal to variance of YBR bar. That means the variance using a single auxiliary variable is always greater than the variance using two auxiliary variables, and they are same when rho is equal to 1, that is the study variable is perfectly positively correlated with both the auxiliary variables. So now consider for the second case. Comparison between the ratio estimator and simple mean estimator. The ratio estimator using one auxiliary variable, that is usual ratio estimator with simple mean estimator. We have variance of the usual ratio estimator YR1 bar equal to 1 minus F by N y bar square C0 square plus C square minus 2 rho 0 C0 C, and variance of y bar, that is equal to 1 minus f by n y bar square c0 square. So now consider variance of y r1 bar minus variance of y bar. So this will be equal to 1 minus f by n y bar square into c square minus 2 rho 0 c0 c. So now the usual ratio estimator y r1 bar using one auxiliary variable will be preferred to the simple mean estimator y bar if c square minus 2 rho 0 c0 c, this variance, this is less than 0, because this variance will be less. So that implies c minus 2 rho 0 c0 is less than 0. That implies c less than 2 rho 0 c0. That implies c by c0 2 is less than rho 0. So that implies rho 0 is greater than 1 by 2 c by c0. That means when this condition is satisfied, that means the correlation between the study variable y and the auxiliary variable x1, if it is greater than 1 by 2 c by c0, then this ratio estimator is preferred to the simple mean estimator y bar. So when c equal to c0, then if rho 0 greater than half, then we prefer ratio estimator. That means when the correlation between the study variable and the auxiliary variable is greater than half, that means both the variables are highly positively correlated, then the ratio estimator, usual ratio estimator, is preferable than the simple mean estimator, that is the estimator using no auxiliary variable. Now the third case. Comparison between the bivariate ratio estimator with simple mean estimator. The variance of simple mean estimator equal to 1 minus f by n y bar square c0 square, and variance of bivariate ratio estimator is equal to 1 minus f by n y bar square c0 square minus 2 rho 0 c0 c plus c square by 2 1 plus rho. Now the bivariate ratio estimator will be superior to the usual ratio estimator y bar when variance of y bar is greater than variance of y bar. Now that is, we have this is greater than this, that means this minus this greater than 0. So we get minus 2 rho 0 c0 c plus c square by 2 1 plus rho is less than 0. That implies rho 0 is greater than 1 plus rho by 4 into C by C0. Hence, under the above this condition, the bivariate ratio estimator is superior to the simple mean estimator y bar. That is, when this condition is satisfied, then only we can use bivariate ratio estimator. Otherwise, we prefer simple mean estimator. Now, in our next video, we shall generalize this bivariate ratio estimator to the multivariate ratio estimator, that is the estimator using P auxiliary variables. Hope you have enjoyed the session. Thank you.